Hello everyone, my name is Peng Huang and I come from Zhejiang University. This work, Secure Headset, a practical privacy protection system for real-time voice communication, is collaborated with Kunpan, Qinglong, Wang, Peng, Lilu, Zhongjie, and Ren. So let's get started. Voice communication are everywhere. People could communicate with others remotely with voice call, video call, or online conference. And I believe that everyone here have used the voice communication applications. Until 2025, there are more than 3 billion active users per month for WhatsApp, more than 1 billion for WeChat, and more than 100 million for Line. These numbers are still increasing for each year. During the voice communication, we need to first send our voice to the application, such as WeChat and WhatsApp. The application will send our data, our voice data, over the internet, and then play back the voice to the other user. But the problem is, since most voice applications are closed-sourced, they are totally black box to the users. So we send our voice to them, but we don't know if he will store our voice and analyze the content, then steal our privacy. Besides, since there could be software flaws in any application, attackers may exploit flaws and then eavesdrop on user voices. So the problem is we need to use the application, but the application itself could be the attacker. To protect user privacy under this scenario, recently some researchers adopted encryption before sending the data to the application. This method always requires the two users to use the same extra hardware as an audio relay between the user and the application. During the communication, before sending the user's voice to the app, the hardware will first encrypt the data and then send the encrypted data to the application. So in this scenario, even the application can get the encrypted data, they cannot decrypt it. So they cannot steal the user's privacy. Similarly, in the receiver side, before playing the voice back, the application would, but the extra hardware will first decrypt the data. But the problem is the audio transmission process in most or in all applications, in all voice communication applications are lossy. Once they got the audio signal, the application will process them lossily, including noise suppression, audio compression, and during the transmission, there could be packet loss. Besides, all of the voice application is optimized for human voice. Other audio signals, such as music or noise, would be suppressed for better voice quality. So the lossy process would corrupt the encrypted data. Since the decrypted process always requires high integrity of the data, the decryption process is nearly possible in this scenario. So here is an example of the spectrogram of the encrypted data. The work is published in 2022. In the original paper, in this paper, the encryption method is robust against some audio compression process, but they have not considered the noise suppression in practical applications such as Telegram. So as a result, the encrypted data is identified as noise and suppressed, and the other user is not possible to decrypt the data. So in this work, instead of encryption, our main idea is to use voice obfuscation to protect the user's voice privacy. The idea is quite simple. Instead of encryption, we add obfuscation noise to the voice to make it unrecognizable to both the machine learning models and the human ear. And in the receiver side, we remove the noise and retrieve the original voices. But however, since the noise is additive, it could be removed by deep learning models if the attacker is powerful. Besides, the attacker may have the knowledge of our system. So if the application is the attacker, they could obtain the obfuscated voice and the knowledge of our method With the knowledge, he could train a customized denoising model. And then with this model, it is possible for him to remove the noise we add. So the noise we used should be robust against such customized denoising model. So traditional noises such as white noise or bubble noise, they are widely used in several scenarios. But they can be easily removed by pre-trained deep learning models. For example, here are the spectrogram before and after processed by a pre-trained model. The result indicates that these types of noise could be removed, and we cannot use them. Besides, in our scenario, with the white box knowledge, the attacker could train a customized model. So in this work, we propose a new type of obfuscation noise named foaming-based denoising-resistant noise. The main idea is to make the noise similar to the voice, and then they could be coupled and hard to be separated. To generate the noise, we first collect a lot of raw data, select the raw data randomly, and concatenate them into a noise series. The raw data are supposed to have similar timbre to the user's voices. So to collect such data, we could first get the user's timbre with his voice, and then match the most similar voice data from some public data set, such as Libre Speech, Giga Speech. And then, since the human voice is also the concatenation of foaming, including words and consonants, our noise have similar structure to the user's voice. These two similarity makes our noise easily coupled with the user voice and hard to be removed. To validate the robustness, we simulated the most powerful attacker who have the white box knowledge of our method and train several customized denoising models targeting on different types of noise. Results show that when the number of word series is larger than 2, the word error rate of the attacker will be always higher than 17%, which means the noise is hard to be removed. Then, based on this type of noise, we design our system with two simple phases. On the offline registration phase, the system or the headset should register itself to a public certified authority and get its certificate. And the user should register himself to the headset with his voice data. The voice data is used to get the user's voice timbre for generating voice data of the obfuscation noise. It should be noted that the offline registration phase has to be performed only once for each headset and each user. In real-time protection phase, the user could use our system as a normal headset in voice communication process. After turned on and connected to the device, our system would automatically execute the full process. First is the key and the information sharing. These two, the two headsets would first share their public key and then share the user timbre and the session random number. This information is shared by encryption with the public key, and after received, the other user would decrypt it with his private key. So if the man-in-the-middle attacker could not decrypt this information, then the timbre and the session random number are used to generate the obfuscation noise for both users. In the voice obfuscation process, the system simply generates noise based on the user's timbre and the random number, and then add the noise to the voice before send the voice data to the application. Then for the channel state information estimation process, we mainly focus on the frequency response and the compression loss ratio of the communication channel. We found that the frequency response are stable in each application, but there are more differences across different applications, so as the loss ratio. So since the channel state is relatively stable in each channel, we can estimate the channel state information with a one-time probe exchange process at the start of each communication. So then we need to retrieve the original voice from the obfuscated voices. Generally speaking, deep learning-based methods could achieve better performance than signal processing, but in our scenario, deep learning model sometimes it's hard to achieve real-time processing in some edge device, for example, some headset. So we propose a signal processing-based voice retrieval algorithm based on spatial subtraction. First, we will segment the noise stream and the audio stream. The audio means the voice after obfuscation. We segmented them into blocks, transformed them into frequency domain, and then compensated them with the frequency response we estimate. Then we calculate the retrieved data with voice and the noise by adaptive spatial subtraction. The parameter alpha is optimized for each segment by minimizing the energy of the retrieved voices. For more detail, you can refer to my paper. So then we will further filter the residual noises with the loss ratio, which is also estimated in the channel state information estimation process. So in our evaluation, we test two channels, both the voice over internet protocol channel and the voice message channel. We test 8 widely used applications, including WeChat, Line, WhatsApp, and Skype. The system is implemented in Python and is run on a Raspberry Pi 5. The prototype cost less than $100. We first test if our system can prevent attackers from obtain information from the obfuscated voices. So we consider two types of attacker. The type A and B, they have no knowledge about our system, so they would use public open source the denoising model to obtain to process the voices. And the type C attacker, they know the detailed information of our system. They will Cheng customize the denoising model. Results show that our system could prevent attackers effectively. The recognition accuracy is lower than 25% for any type of attacker in both VoIP channel and the voice message channel. Then we test if our system will affect the voice quality during voice communication. For the user, the recognition error rate should be as low as possible. And the results show that in 6 out of 8 tested applications, the recognition accuracy is higher than 75%. And in WhatsApp and WeChat, the error rate is a little bit high. And yeah. Then we have also tested the performance of our system on the different network bandwidths and the different communication device. And the results show that these factors have limited impacts on our system. Then we also tested the time delay induced by our system. To achieve real-time processing, the time consumption for each audio block should be smaller than the length of the audio block. Results show that for 16.4 millisecond audio block, the time consumed for processing is about 17 milliseconds, which is far more shorter than the audio length when the system is running on a Raspberry Pi 5. Besides, currently our system is implemented with Python. In the future, if we can implement our system with more effective language such as C, the time consumption could be further reduced. So in conclusion, in this work, we introduced secure headset to protect voice privacy with commercial off-the-shelf edge devices. And the system works well in commonly used voice communication applications. So that's my presentation, and thank you very much.
Okay, great work and great presentation. This is Leming from Hong Kong PolyU. My question is that you mentioned that the encryption and decryption method is typically suffered from the network issue. So I'm curious that why adding noises is not suffered from network issues. Yeah.
That's a good question. So for encryption, the data integrity is very important. Although there are some methods. For example, in some encryption algorithm, if only one data bit is flipped, the decryption process may not be feasible. And there are some papers that focus on distortion-tolerant encryption process, but they are not feasible in practical scenario with high distortion. Well, if we use the noise obfuscation, there are two main reasons. First, after obfuscation, the audio signal is still it still have voice structure. So the communication application will not identify it as noise, and so it would hard to suppress the data. And second, the distortion on the audio signal will left some residual noise in the retrieved voice, but it would not affect the recognition process. So indeed, our system will degrade the voice communication quality, but it is usable. Yeah.
Oh, okay, I see. And another question is, what if the attacker is deploying inverse the diffusion model, that is, remove the noise step by step, similar to that? Yeah.
Yeah, that's also a good question. And currently, we only consider the attackers use transformer-based model to separate or enhance our voice. If with diffusion model inherently are better denoiser than transformer. So I think maybe with this technology, the attacker could retrieve more content. But honestly, I haven't tested that.
Okay. Thank you very much. Great work.
Thank you.
Miles from UC Thank you for the really interesting talk. So maybe I missed it, but I have a really simple question. Does this only work between two devices?
Currently, yes. We only consider two devices. So if there are more than two people, such as voice conferencing, currently our system is not feasible.
Okay, and does it only work between two persons?
Yeah, currently, yes, because the noise is generated based on his timbre.
Okay, got it.
Yeah.
Thank you.
I also have a quick question. Does that noise register with the users release any personal information?
It may release some user biometric information, but our system is totally offline.
I see. So you assume that the communication is encrypted, and during the transfer, this information cannot be obtained.
Yeah.
I see. Thank you. Let's give the speaker another round of applause.